Hello everyone! This video illustrates the automatic modeling features available in DistrictLab H Simulation Studio. The video is based on a case study located in the French city of Grenoble, and more specifically in the Scientific Peninsula district. The modeling process begins by importing the data present in the two shapefile layers, which respectively position the consumers and the layout elements of the various pipes. At this stage, it's interesting to note that, as can be seen in this zoomed-in image, the layout elements present in the shapefile need not be contiguous. DistrictLab automatically corrects these geometric inconsistencies. In the same way, substations need not be joined to the network layout. In the same way, DistrictLab will automatically reconnect all these elements during the import stage. This stage is set by a number of parameters that can be saved in a configuration file that can be recalled from one session to the next. The import parameters define the link between the data present in the shapefile layer and the data expected in the DistrictLab model. In the case of pipes, the parameters simply impose an internal diameter value of 100 millimeters. Any data present in the shapefile layer is ignored here, and this default value will be resized at a later stage. Pipes can be imported in simple mode, where each polyline produces a single pipe. In this example, however, we use the doublet mode, where each imported polyline produces a doublet of supply-return piping elements. Consumer import settings can also be based on a configuration file that can be saved and reused from one session to the next. Without going into the details of parameterization, this video illustrates the possibility offered to the user of relying on scripts that optionally position an intermediate processing layer between the data present in the shapefile and the data to be received by DistrictLab. In this example, the script is called Pipe Model From Sizing. The purpose of the script is to transform the sizing power value into a diameter value by means of a number of elementary equations and a speed limit threshold, here set at 2 meters per second. For the other parameters, the default settings are sufficient at this stage, and the consumers can be imported in a second step. Once the pipes and consumers have been imported, they need to be connected to each other. The individual pipe elements, initially disconnected from each other, can be automatically assembled. A geometrical tolerance, here set at 50 centimeters, is set to allow non-jointed pipes to be connected. The second step is to connect the consumers to the network. The default settings are sufficient for this. Other operations are also possible, such as eliminating nodes to automatically simplify imported models, or simplifying layouts to highlight changes in pipe direction. At this stage, there are still a few elements to be added to make the model eligible to simulation. First, we need to add a simple piping element to form the production plant. This element connects the network's return node to its starting node. We set a default diameter for this pipe of 100 millimeters, which will be automatically resized by the tool according to the consumers declared on the network. The power plant is represented by a pump, regulated to ensure a minimum differential pressure of 1 bar across the network's consumers. The model is then completed by the addition of a generator, regulated in supply temperature, with a fixed set point or one derived from a heating curve. For the example, a heating curve covering the range minus 11 degrees Celsius to 15 degrees Celsius outdoor temperature and 95 degrees Celsius. 75 degrees Celsius forward temperature can be programmed. Finally, it is necessary to add a pressure maintenance unit. This is achieved by means of an imposed pressure boundary condition. This is an open node where the user sets the pressure, here 1 bar, and an external temperature in the event of fluid entering the network via this node. The model is now ready for simulation. Simulation takes place in the so-called post-processing mode, which allows you to parameterize simulation cases called problem. This takes place by defining the network models to be taken into account, the dynamic boundary condition files to be considered, the start and end dates. If the end date is not entered, the simulation will cover a 24-hour period by default, a time step, typically 3,600 seconds, and a few numerical parameters, such as whether to start the simulation with a static time step. Switching to simulation is conditional on the positive execution of a verification step. The simulation can then be triggered. At the end of the process, the results obtained are automatically loaded and can be examined, notably through graphical themes. In this example, the theme used colorizes piping elements in relation to fluid temperature and consumers in relation to the degree of opening of control valves. The plotter view allows you to plot and compare the temporal evolution of all the variables provided by the simulation engine. The graphs show that all the heat called for has actually been delivered by the network. The final step in this demonstration consists in automatically resizing the distribution pipes on the basis of the simulation case just calculated. As an example, we declare here that all pipes in our model are resizable by setting the SIZ resizable parameter to true. It is also necessary to set a threshold for the maximum linear pressure drop value. Here, we set this threshold at 200 pascal per meter for all the pipes in the model. But this criterion could be adapted according to the pipe's position in the network. The resizing functionality is triggered by specifying the simulation cases involved in the resizing. Once completed, an execution report summarizes the process. Here, 84 pipes have been resized, and a table details all diameter modifications. It is then useful to simulate this case again to examine the new results. We can see that pipe diameters do indeed decrease from the production plant towards the extremities of the network, as would be expected for a network of this nature. To sum up, this video shows that in just a few minutes it is possible to start from a blank model, import data initially present in shapefile type layers, simulate a realistic case, and propose consistent diameters based on an automatic resizing module. The result is a realistic, consistent network model. Thank you for your attention.